we can increase the switching frequency because the switching losses can be reduced. So we can reduce the size of passive components, for example, inductors and filters. This shows one example of the inductor size difference. Both one has almost same current rating, but inductance is different. This can be used for 100 kHz operating frequency, and the right side one can be used for 5 kHz operating frequency. So, so by increasing operation frequency, we can reduce the size of inductors very drastically. So soft switching can contribute high efficiency converter and high power density converter. So we are back to a mass concept. This concept is already introduced by Professor Shimada, AC mass concept. And now, so the point is the capacitor voltage waveform is, has a zero voltage period, and the waveform is like that. And we added DC, external DC circuit here, but so this circuit diagrams looks like a conventional power converter topologies, but the difference, the features of this mass concept is the size of capacitor, reduced size of capacitor, and a very unique waveform of voltage in the capacitor, discontinuous DC link voltage like that. And by using this unique waveform, we can achieve soft switching, zero voltage switching. So, I will talk about the very first applications of soft switching technology, industrial induction heating application. As you know, the induction heating is used in cooking in the domestic, but very high power induction heating up to several megawatts installed in steel mills, as shown in here. And this heating method is very good because high efficiency, because the steel is directly heated. It's compared to other heating method like gas furnace. And it has high performance of heating control. We can control easily the input power. High potential. It has high potential for high performance heat control. If the frequency can be changed, heat distribution control can be done. But the conventional converter has no frequency controllability because very big capacity of converters, and the induction heating, the power factor is very low. So they use a series capacitor, so they cannot change the frequency. So conventional converter has no frequency controllability. Variable frequency results in increased semiconductor rating, very big semiconductor rating. This is a demonstration of heat distribution control by changing frequency. This photograph shows a steel plate and coil to heat the edge part of this steel plate. This is a sun view of this steel plate. We can control the heat distribution along, and if you can heat only edge part by increasing frequency. So this is our mass high frequency inverter here. Large semiconductor capacity is needed, but it has variable frequency capability. So this converter has soft switching advantages based on mass concept. So this mass concept makes it possible because reduced switching loss, and this results in reduced semiconductor rating. And high power semiconductor can be used for high frequency. This photograph shows a 90 kVA pilot device. This is made by our students at our laboratory, and heat distribution control introduced in the previous slide was demonstrated in a steel company. And this is a professional product rated with 2.5 megawatt device. The photograph is here, and this is a schematic view of inside of the power converters. 2.5 MVA and some 300 kilowatt system for field evaluation in a steel company. The frequency can be changed from 1 to 10 kilohertz, the variable frequency operation. And high power IGBT devices are used with unusual high frequency. Usually, the very high power semiconductor devices cannot be used for this 10 kHz switching frequency. Usually, one or more or less frequency is enough. But due to soft switching, we can use very high power semiconductor devices to this with this very high frequency. Okay, that was a very fast application of our soft switching technology, and we will go to more general applications. So I will talk about a little bit complex thing. This mass concept can be generate a DC pulse voltage as introduced in the previous slides. From DC voltage, we can generate pulse voltage. And doing same thing, we also can generate pulse voltage from AC line frequency, 50 or 60 Hz, and also can be from three-phase AC system. So by using this concept, we propose a mass pulse link concept. The diagram is shown here. Two converters usually connected via DC voltage source, but our concept is connecting via pulse DC voltage, and the first stage generates pulse voltage, and the first converter is implemented by our mass. And both converters can operate with soft switching, and there is no smoothing capacitor between two converters, so no large smoothing capacitor. So advantages, one advantage is soft switching and no smoothing capacitor. So we can apply this concept, for example, two applications, from DC source to three-phase output, and from three-phase AC line frequency utility line to variable frequency AC output. From DC source, we can apply for motor drive by DC source, for example, electric vehicle, and grid connecting inverter for photovoltaic or fuel cell. And this AC to AC direct converter can be applied for general motor drives and grid connecting of generators. So firstly, I will introduce about the from DC source to AC output system. The advantages already mentioned, no bulky smoothing capacitor and soft switching. And so by soft switching advantages, high frequency can be used and good for reduce the size of inductors and filters. But we have some challenges. No energy storages between the two converters, so it means high performance control is needed, because usually there is many size of energy storage. So if there is a difference of the power flow between two converters, there is no problem. But we have no energy storages between the two converters, so the power flow, strictly power control is needed. And higher peak voltage or discontinuous input current may be problem, but by advanced control we can mitigate these disadvantages. This application is now on a little bit early stage, very small scale experiment in the laboratory. We apply this concept for induction motor drives. This device is made by our students, and we applied for this induction motor rated 750 watt. This is tested induction motor, and this is the generators for load. And this is experimental waveforms. This is current waveforms flowing into the induction motor. Control method has been developed to maintain the voltage and current waveform good. And is now under development, under evaluation. Finally, we have a potential for AC to AC direct conversion from AC line to the variable frequency induction motor drive. There is no smoothing capacitor like a matrix converter. This is well-known concept in the power electronics field. No energy storage between two converters. And soft switching is advantage for matrix converter, and higher output voltage. We can increase the voltage from this voltage. We can apply more high voltage rather than this input voltage. And this project is current status is the first demonstration was successfully done with induction motor drive. This is just a simulated waveform, but now we successfully demonstrated with induction motor. And also developing control technique to achieve good semiconductor rating utilization or more good control performance. So finally, so I would like to mention other applications of soft switching applications of mass. The high frequency inverters, this is already introduced in my presentation. This was first application. The first application was induction heating, but the high frequency inverter is very, very fundamental converter topologies in power electronics field. So there are many other applications of high frequency inverters. Next, I talked pulse link concept and from DC battery source or AC line, utility line to motor drives, variable frequency. This can be applied for variable speed motor drives and AC grid connecting converter for renewable energy or storage. For example, photovoltaic, a fuel cell, or superconducting magnetic energy storages, and generators like engine generators. And additionally, I will skip other fields of these applications. One is active rectifier, AC to DC, mainly AC to DC. This can be applied for general DC power source, like a rectifier for conventional motor drives or other many electrical equipment. And advantages is good input current characteristics with soft switching. It means improved power factor and improved harmonics characteristics. And finally, we are now working with bidirectional DC to DC converter. So this can be applied for DC distribution system power flow controller, DC grid connecting converter for renewable energy or storage, same as this. So this is my last slide. I will conclude my talk. Soft switching and small passive components is key issues, and they result in less heat and compact converter. These advantages were proven in high power induction heating applications. We can achieve variable frequency induction heating with a small electric equipment. The proposed mass converter achieves variable frequency induction heating, which have not been achieved with conventional technologies. Next, I talked about the more general applications, for example, motor drives and grid connecting inverter for renewable energy and storage. This is now a little bit under evaluating, but potential has been confirmed by small-scale experiments in our laboratory. Next step, numerical evaluation of loss and size are needed. This is our laboratory member. Thank you for your attention.
Do we have time for one question?
Shimada-san, I've been very intrigued by the MERS conversion systems. Has it been applied more broadly, and what are the relative cost of it compared to current systems? Because clearly you've defined a very truly flexible system for soft switching and power controls. Can you tell me about its current state of commercialization?
Yeah, as I mentioned, these high-frequency inverters are already made by maker. But other applications are now just in our laboratory, so we cannot compare to other technologies in a cost or size. Yeah. But we confirm the concept, potential.
May I add one comment, if you don't mind? Cost comparison has been done internally at our level, and cost is supposed to be theoretically a lot smaller than conventional PWM controller, because number one, heatsink is not needed, and number two, one less switches are required. So both those cost reduction itself will be about 30% less than PWM circuit. And yet, PWM circuit is already mass production. So cost is already down by a scale of economy. So that's my comment.
Thank you.
It's a simple question that if those of us who want to try and get some of your systems to incorporate, let's say, in one of my microgrid developments, how does one go about doing it? Do we need an MOU with Shimada-san's group and all of that? You know, just that.
Okay. Welcome.
Okay. Thank you.
Well, thank you.
Thank you very much.
Our next speaker is Dr.